Welcome back. In this chapter we talk about man-in-the-middle attacks, especially for Android devices, and this one is absolutely essential because most of the vulnerabilities we encounter in mobile applications, they are not within the activities, content providers or broadcast receivers, they are within the network services of the application itself. There are a lot of different setups on how to perform a man-in-the-middle attack regarding to an Android device, but many of them have huge weaknesses. They act just like a proxy for HTTP and HTTPS requests. For example, if you go into your Wi-Fi settings, you can define a proxy over here. And if you insert the IP and listening port of your Burp instance, yes, then you have established a man-in-the-middle connection regarding to your web services, but you will miss a lot of stuff. For example, if this application uses SSH, SQL or MQTT or SIP, you do not see this traffic. This traffic will be not forwarded to your Burp and therefore you definitely will miss it. And this is something we do not want to have. We want to see all. But beside this fact that we miss a lot of stuff, we also do not have control over the network traffic itself. For example, we do not have control over DHCP and DNS. So this is the reason why I choose a different setup. And the setup I'm using provides you full control over DNS, DHCP, and it can also intercept and manipulate every connection the device is establishing. For example, if it's using SIP, MQTT, SSH, SQL or whatever else. So this is why I choose this type of setup. But before we dive into the setup, let's first talk about man-in-the-middle attacks itself. So what is a man-in-the-middle attack? And to be honest, I do not have an official description for this right now. But this attack simply means we are the man in the middle of a connection. So in between two devices. In most cases, it means we are in between the In most cases, it simply means we are in the connection of a router and a network device, for example, the smartphone. If we are in between this connection, we can analyze, sniff and also manipulate these packages if they are not being encrypted. We talk about SSL later on, but for now, let's focus on man-in-the-middle itself. So now we know, okay, what a man-in-the-middle attack is, but how can we establish such a connection? There are a lot of different setups out there, but we focus now on the most basic one, the ARP cache poisoning attack. But don't worry, ARP cache poisoning is not part of our man-in-the-middle setup later on. This is just a good example to get familiar what a man-in-the-middle attack is and how it works. This is why I picked it as an example out here. Alright, so before we can understand how an ARP cache poisoning attack works, we need to understand how client A is communicating with client B. So what is happening on the line that these two can communicate with each other? There has to be some exchange of information, and this is something we take a look on right now. But don't worry, we do this on a very high level and we do not go too deep into detail. Alrighty? Okay, so let's switch back to the slides. Alright, so here we have our basic network setup. We've got the router, we've got two laptops and a mobile device which is connected via Wi-Fi. Every device has a network card, and this network card has a MAC address. This is a unique identifier which is branded into your card. So this MAC address only exists once. There will be no duplicate of this number over here. A MAC address consists of 6 bytes, and the first 3 are regarding to the vendor ID, and the last 3 are regarding to make this MAC address unique. So this means we can theoretically run out of MAC addresses. We have a number from 2 square 6 times 8, which is, well, it's quite a lot. So even by having now all these IoT devices, connected cars and all this kind of stuff, we do not run out of MAC addresses very soon. This is something we do not need to worry about right now. Beside this MAC address, there's also an IP address, and this is something that is being assigned via DHCP or statically. So in our case, we have a router which is running a DHCP service, and this router is providing IP addresses to every connected client. In our case over here, we have a class CNETs, which means we've got 192.168.1, and then we can provide IP addresses to connecting hosts from 2 up to 245. The rest is being reserved for broadcast and gateway and other stuff. Alrighty? Okay, so this is a recap of networking on a high level. Now let's say the client over here, this is client A, and client A wants to send a message to client B over here. Client A knows the IP address of client B, and this one is .14. But what client A does not know is the MAC address, and this is also absolutely essential to prepare this package. We have an Ethernet frame, and this Ethernet frame needs to have the MAC address of the destination host. So how can we get this MAC address? And this is where ARP kicks into. ARP is the address resolution protocol, and it has a different type of opcodes. One is, for example, the ARP request. And ARP request is simply a network package which is asking for who has this address. And this kind of package is now being crafted by client A. And it's being sent into the whole network, so to the router, and the router is broadcasting this into the whole network. This package is now being broadcasted, and it receives the smartphone via Wi-Fi. The smartphone is taking a look into this package and replies with, "No, this is not me." Client B also receives this package and is also extracting these information and realizes, "Ooh, that's me." So client B is now preparing an ARP reply package. This ARP reply package contains the IP address and also the MAC address of this client, of client B. Packed with these information, this package is now being sent back to client A. Client A receives this package, takes a look into this, and now checks, okay, I've got the IP address, but now also the MAC address of client B. And client A is also very lazy, so client A do not want to ask for this over and over again. Therefore, client A is saving these information in something called ARP cache. This is the resolution of IP address and MAC address. So the next time client A is sending a message to client B, client A does not have to ask for this once again. So client A is simply taking a look into its internal ARP cache and realizes, okay, this is the MAC address of client B, and this is the address I have to use in my Ethernet frame to wrap this around my package. Okay, so this is how the exchange of information works on a very high level. After getting those information, client A is now able to communicate with client B and can simply prepare a message and send it to client B. This package is now being wrapped into an Ethernet frame, and this Ethernet frame contains the destination IP and also the destination MAC address, which is now known by client A. Okay, so far so good, but what if your PC breaks? For example, you have been caught cheating on a huge LAN party, and your PC will be thrown out of this LAN and completely breaks into single pieces. Your network card? Absolutely gone. This means your network card is not available anymore. The client still has this reference in its ARP cache, so regarding to this IP address and this MAC address. And now let's also imagine a new client is joining the network, and the router is recycling the IP address of the other client. So the new client has of course also a MAC address, but this is now different from the other one because MAC addresses are unique, and the client now receives the IP address from the previous client. So in this case the ARP cache is now invalid. How can we fix this issue? Well, after client A has tried several times to connect to client B and it's not available anymore, client A is performing the same approach once again. So client A is preparing an ARP request and sends it out into the network. Client A is asking for, who has this IP address? Please tell me your MAC address. And this package gets broadcasted into the network. The smartphone still responds with, no, it's not me. But it actually sends no package. This is just an information for us that it's not the smartphone right now. There will be no package regarding to an ARP request. But client C, who has now this IP address, responds with the MAC address of its own. So client C is responding with an ARP reply package. And this one now contains the IP address and also the new MAC address of the client right now. This package will be sent to client A. Client A receives this package and also updates its internal ARP cache. So the old MAC address will be deleted and the new one will be inserted. And this is how an ARP cache gets updated. And this is a very, very important step regarding to a man-in-the-middle attack, regarding to ARP cache poisoning. Because the address resolution protocol has been developed in 1980 something. So I'm absolutely not sure when exactly. But during this time, no one has thought about security in a protocol like this. And this is where the vulnerability relies, in the ARP protocol itself. And this is something we are going to investigate right now. So how can we take advantage of this type of tech on updating an ARP cache? Well, we will find out right now. Alright, so now's the question, how can we abuse this as an attacker? How can we get into this connection in between the smartphone and the router right now based on ARP packages? So here we have the smartphone with the .10 address, and we also got the router which has the .1. So the router also acts as a gateway. This connection has been established and both devices have created their own ARP cache. So the smartphone has the ARP cache for this router with this MAC address, and also the router has created its own ARP cache for the smartphone, so with the MAC address of the smartphone. Okay, now the attacker kicks in. The ARP cache has been set up and here's the attacker right now. The attacker also joins the network and receives an IP address, but this is not the most important part. The most important part is that the attacker is now creating an ARP reply package. Yes, you heard absolutely right, an ARP reply package. Not a request, a reply. And this package contains now the address of the router. And now there's the clue. The attacker is filling this package with the MAC address of the attacker itself. So not with the MAC address of the router. And this package will be now forwarded to the client, so to the smartphone. The smartphone is now receiving this ARP package, but the smartphone says, well, I didn't ask for this, so please don't bother me with this. But we keep sending it over and over again. And based on the protocol itself, there's no kind of authorization or authentication or whatever. So by replying this package over and over again, after a while the smartphone accepts it and will update the ARP cache for this entry. The device now thinks that the attacker is the real gateway. All the traffic from the smartphone is now being forwarded to the attacker, and that's all the attacker has to do. The attacker simply has to flood the mobile device with a lot of ARP reply packages, and this is the, let's call it vulnerability in this protocol, because a reply package doesn't require a request before. And this means we can simply create a reply package without having a request from this client over here. And by replying this package over and over again, the ARP cache entry in this device gets updated regarding to the poisoned MAC address. Alright, and that's all. This is how we can establish a man-in-the-middle connection. So, as an example, the smartphone right now is opening a web page. For example, let's say example.org. We will learn how to deal with this later on, so how we can create our own certificates, apply them to the device, and also intercept SSL traffic. But for now we want to focus on man-in-the-middle attacks regarding to ARP cache poisoning, and therefore we do not need to make it more complex than it really is. Alright, so the client is now opening or trying to open the website example.org. This is now being crafted as a package, so as an HTTP package. The client, the smartphone in this case, is forwarding this to the router, but not to the real one, to the attacker, because the smartphone thinks that this is the gateway right now. The attacker receives this package and can now analyze and also manipulate it. So for example, if there are some user credentials in there, or the attacker can also send a different type of requests to the original systems. Stuff like this. So we are now within a man-in-the-middle position right now. All the attacker needs to do is to forward this to the real router and update the Ethernet frame. We skip this part right now, but this is not a big deal. Okay, so the package has been arrived at the router, and the router is now forwarding this into the internet, to example.org. Example.org is now replying to this package, and it's sending the response regarding to this HTTP request. The router now checks the package, and the package is now for our attacker machine, because the attacker has replaced all the necessary frames, for example the Ethernet frame. So the router is forwarding this package right now to the attacker. The attacker can then inspect it once again and also manipulate the response. For example, insert some hidden form fields, inject JavaScript keyloggers, stuff like this. After performing this type of action, the attacker now only needs to forward this package to the original source, the smartphone itself. But the smartphone doesn't even realize that this one has been not routed through the original gateway, it has been routed to the machine of the attacker. So the smartphone takes this package and renders it in its browser, because it's the response of the original HTTP request. Therefore for the smartphone everything is fine, the attacker is also happy, and the gateway also didn't realize that this package has been originally sent from the smartphone itself. So for every device in this connection over here, it seems to be fine how this request has been handled. Alright, so this is how a man-in-the-middle attack works, but as already mentioned, this attack also has a lot of weaknesses. For example, we need to flood the entry of the smartphone permanently, because it could happen that the original gateway gets back into the ARP cache by providing new packages. Therefore, we have to permanently send these ARP reply packages, which causes an overload, and we will definitely miss some packets of the smartphone itself. So therefore, if you do not have control over a device in this network over here, then yes, this might be the only solution. Okay, there are some other possibilities, for example, like DNS spoofing, where we just answer faster than the original name server and things like this. But yeah, most of the time it's the same approach. But yeah, all of them are not super reliable, so it might be the case that the device changed back the connection, and this might be just for some few requests until we get it back again. But these few requests will be missed in our traffic, and this is something we do not want to have if we analyze a system. Therefore, we have a different setup, and this is something we take a look into in the next video. If you have any questions regarding to ARP cache poisoning, DNS spoofing, or other type of man-in-the-middle attacks, then please write me a message. I'm super happy if I receive feedback on certain topics, and yeah, if you're stuck at the point, I try my best to help you out on this. Alright? Okay. In the next video, we take a look at a different type of setup. And this setup gives us full control over the whole network and also the traffic in this device without permanently flooding this device with malicious packages. Therefore, I'm really looking forward to see you in the next video.